Okay, we'll go ahead and get started. Again, it's kind of funny you guys are all in the back. It's just like class. It's kind of funny, but anyways, I hope I don't smell. If I do, let me know, okay? So welcome to my talk. This is a brief history of mathematics, but I'm trying to make it as brief as possible, okay? So hope it doesn't go too long for you, but because mathematics is a long history, and I'm going to try to focus a lot on the ancient history of mathematics and then some of the modern stuff, because actually modern mathematics is just a tremendous amount of work that I just have no possible time to go through. So what we're going to start off is we're going to start off with the birth of mathematics, and really what it is it's not just mathematics, it's actually mathematics and science. And because it turns out that it's math and science together that actually are basically fundamental to what we are as human beings. Some things, some visceral aspects of ourselves are shown in mathematics and science. And that's how, and you're going to see later, that every complex society in some way or another has developed some form of mathematics, science, and as societies get more and more complex, these are required just to keep logistics in society. Okay? So what I'm going to do is start off, here is just some ancient numbers, but we're going to start off right from the scratch. Okay? The origin of mathematics and really how to get started. And it starts with two basic principles. So, I'm going to assume that you know really nothing about mathematics, other than numbers and what you've done in school. But actually, the origin comes from really our principles of quantity and space. That's really fundamental. If you think about it, what's most important to you? We talk about time, but it's really space and quantity. How much? Are we outnumbered? Are we undernumbered? These are basic concepts we go through every day. We don't even think about it. Okay, but it's hardwired really within every animal. You think about it. If you get too close to a cat, what happens? A wild cat, she runs away. It's the same thing. Every animal has this sense of really quantity and space. But really, it was man or human beings that really uniquely built upon these basic mathematical principles by using logical deductions, and it creates the complex subject we have today. So it's really fascinating that how we could take simple ideas that every animal, every creature understands viscerally, and take it, create abstractions, and create the subject we have today. So it's actually pretty fascinating, and it really comes again down to quantity and space. Pretty basic, but very important. So primitive man, and I always say this cartoon is probably my favorite mathematical cartoon, and maybe you can't see it from there, but obviously these are three students, and this is the teacher, and the top one says, man plus sphere plus animal means fat man. And then you got animal, no sphere, plus animal equals fat animal. So it's kind of funny, right? But it's just an example of some goofy mathematics, and who knows where it really started. But again, hunters and gatherers, we unknowingly used mental statistics. We quickly sized up quantity, as I talked about, because and quality of food, herd of animals, things like that. This was basic to our survival, okay? And what really started changing man was the discovery of agriculture. Because when we started to discover agriculture, we fundamentally transformed ourselves from a transient species to actually one that settled down to create societies. And it's that aspect that really fundamentally changed us. See, once you set down and you're now static, you're in one location, what ends up happening? You got agriculture, so your population grows, and it turns out just to survive, we develop math and science naturally just to cope with that. So it's actually just a process, really, in my opinion, starts from agriculture. That we just sort of discovered that, if we grow plants, we can have, we can keep the food, make it more stable food supply. And because of that, our population grows. And because of that, that creates the situation such that we need things to help us survive. And math and science being one of them, okay? And This also created the need to observe the environment, when to grow food, religious holidays, which I'll talk about later, and navigation. And one thing we don't realize about navigation is that's extremely difficult. It's not an easy thing to navigate. We take it for granted today. We have GPSs and we have the globe, a map. People never had that. So if you have a small group in the middle of the bush and you decide to go off somewhere, how do you get back? We don't think about that. Okay? So these things we created over time by taking fundamental ideas, create logical deductions, and create more and more complex systems. So primitive man is the start of this. Okay? And so let me give you some fundamentals of mathematics. Really, the two big ones is counting. Now it sounds kind of goofy, right? We just go 1, 2, 3, 4, so on and so forth. But actually, this is a modern science of combinatorics. And of course, Tina here being a statistics person, that's some of the hardest things for people to do. Be able to count. Probability really is, it's really about counting. And actually, counting is a difficult thing, believe it or not. It's not just, literally going 1, 2, 3, 4, so on and so forth. But this idea of looking, now start to categorize things. So here you got 3 white sheep and 3 black sheep. We start categorizing quantity of objects, the magnitude, physical quantity. And then from there we start talking about cardinality, 1 to 1. So we realize we have 10 fingers. So I can say, okay, 1, 2, 3, 4. I start making abstractions. So it starts from just basic observation, and then we turn it to abstractions. And this is what cardinality is. It's a one-to-one correspondence with physical tokens, finger positions, pebbles, anything, sounds, written symbols later with numbers. So it just starts small and it keeps building. Okay? The key to the development of mathematics really comes through 3 basic things. And you're going to see this over and over again. And this is really, again, an introduction to this whole topic. But we tend to have a very Eurocentric point of view. And this is unfortunate because we tend to forget a lot of the great advances made by Asian cultures, African cultures, and early Americas. I'm going to show you just a little bit about early Americas and a little bit from Africa. I don't have much time to talk about that. Certainly Asia, we'll focus more in Asia. But the 3 things that develop mathematics, and I think this is kind of surprising to a lot of folks, religious beliefs or ideas. We tend to have this, this feeling that it's science versus religion. It's not always true. In fact, it really required, the religious beliefs were fundamental to the development of math and science. For example, astronomy and astrology, human proclivities, ideas, space quantity, hierarchies. This all is in mathematics. We talk about 1, 2, 3. What's that? Hierarchies. Top and bottom. Low and high. These fundamental ideas are involved in mathematics, and the idea of looking upwards, something greater than ourselves. That's religion, right? But it also finds itself in math and science, especially mathematics, looking at how can we define the world, using using things that we know, like how can we make more sense of the world, Basically what we're trying to do is learn about ourselves by learning about the world, okay? Practicality, obviously this is one that most people think about. Predicting seasons, tracking cyclical changes, creating calendars. This is, every society has some way or not created a calendar, okay? Why calendars? Talk about that a little bit later, but really calendars are about, growing seasons. Again, if we have agriculture, we have seasons, so you got to grow stuff. What's the best time to grow things? If you have a calendar, what's that mean? You've got to look up to the stars because you see different patterns. You start putting things together to predict future events. Okay? Obviously, building infrastructure as it gets more and more complicated. And market economies, money. Obviously, we need that. Okay? And bureaucracy. Okay? Government taxes. What's the old saying? Everything is sure, there's only a couple things that are sure in life. Taxes and death. Okay? So we're going to get taxed. Funding armies. And management of populace. Again, let me just take you through a basic scenario. You have a group that's discovered agriculture. You start growing food. What happens? They grow larger in population. Okay? Another group over here does the same thing. They grow larger in population. What happens? Now people start raiding other people. If someone raids you, what do you have to do? You have to create an army, right? You have to create some way to defend yourself. Well, how are you going to do that? Now you have some people growing food, some people defending, your territory. Well, how do you defend territory? Well, you've got to pay them. How are you going to pay them? Well, they don't have time to farm, right? So you've got to raise taxes. Well, how do you raise taxes? You've got to go to the farmers. Say, okay, I want some of your grain, I want some of your grain. How do you do that? Well, maybe you have a larger farm than this gentleman over here. Is it fair to tax him the same as this person? So now you need to know what area. So how do you calculate area? Understand how it works? You see, so you develop area. That's what the Egyptians did, which we'll talk about in a few moments. So that is just a simple example of how science can develop. And it's just a necessity. Mother of inventions come from necessity. Okay, so religious beliefs and ideas, practicality, and bureaucracy are really the three drivers of math and science. I'll focus more on math, but until about Galileo and Leonardo da Vinci, math and science really are kind of one and the same, in some respects. Okay? So that's very important. Religious beliefs, practicality, and bureaucracy. Okay, so just I'll give you a couple early examples of mathematics people don't know about. One's in Africa, there's two. It's the Labongo bone and Shango bone. Interestingly, it's one of the earliest known uses of measuration and calculation. And it's extremely old. Look at this, 35,000 BC. 25,000, that's what they guess. It's really, really old. Incredible. And this one here is discovered in Swaziland, probably uses a measuring device. And this one, the Shango bone, which is here, they think at one time it may have been the prime numbers, but actually it was a 6-month lunar calendar. That's what they guessed. So clearly people, even in those remote cultures, had some way of, measuring. Calendars were important to them. It's just every society, in some level or not, you're going to see this. Okay. Again, not a lot of stuff here. It's very old. Who knows what they had? This is all we could find. I mean, who knows how advanced these societies were? Okay, Mayan culture. Most of you have heard about the Mayan culture. I'm not going to spend much time on these because we don't know a lot about them, but in the Mayan culture, Mexico, El Salvador, these folks were in early Americas, cut off from the rest of the world, yet they still had a number system, and it was base 20. Today we have a base 10 number system, right? 0 through 9, okay, that's what we have a decimal decimal base place value system, number system. They had a base 20. They used 10 fingers and 10 toes. Because, they never wore shoes, right? So they counted with their feet and also their hands. Really interesting here. And they also were one of the first folks to talk about number 0. And I'll describe why 0 is really important. It really wasn't until the Indians that we had 0 as a number by itself. People just considered 0 as nothing, and I'll talk more about that, why it's important for 0 to be a number. And here's an example of a number system. And I find this very fascinating because these folks came up with this, without any outside influence that we know of. And they used a cocoa bean as 0. And then a dot is 1, 2, 3, 4. 5 became a bar. And then you go again. You got the bar plus 1 is 6. 7, 8, 9, 10 is 2 bars. And again, you can follow 11, 12, 13, 14, 15, 3 bars. Go right to 19, and then look what we have here. They're stacked, okay? So you have a 0 here, and this is positional. So this dot means 120, okay? So 20 and 0 is what? 20, right? Just like if I have 100, what's that mean? You have 1 100s, 0 10s, 0 1s, okay? So they just stack them this way instead of this way, okay? So now these two numbers here means 20 and 1, 20 and 2, 20 and 3. Understand? So it's pretty incredible what they had. And I don't have a lot of time to go over Mayan culture, but they developed a calendar. They built incredible things using their knowledge of mathematics. And it's called the Vestigial system, base 20, positional numerical system, similar to what we have today. Okay? All right, so what I'm going to do now, I'm going to give you some scope of ancient times, and I'm going to go through some countries like Egypt, Babylon, or Sumeria. We're going to move into the Arabics, and then into China, India, and move from there. Okay? So really the scope of mathematics in ancient times. Because if you know the subject today, a little bit, it's extremely complicated actually. Very complex. But basically most cultures focused on geometry. Geometry, Egyptian, Babylonians, and Greek. Geometry in the Greeks, what they did is they used a compass, okay, and a straight edge. So that means they didn't use measures, they didn't use a ruler to measure anything. They had a compass, like, to make a circle, you spin around to make a circle, used a compass and then a straight edge. And they were able to come up with some incredible things in geometry. Number theory, how do numbers work, and all the possible combinations and different things. It's a big subject today, okay? And then, most importantly, probably algebra. It started with the Chinese and Indians, but really it was developed with the Persians and Arabs, and we'll talk about that later. That's really the scope. It wasn't until after the Renaissance that math started to change, okay? So that's really the scope that you see in ancient times. Okay, so let's start off with Egypt. Egypt's one of the oldest cultures we know of, and again, remember I was saying what developed mathematics? Well, you're going to see this theme come up over and over again. So with the Egyptians, again, they reached a high point in Egypt at a very early time, around 3000 BC. And as you know, the Nile floods dramatically every year. So it was really important to know, right, when the Nile would flood or not. Because when it flooded, okay, it would bring lots of good nutrient earth to the land, flood the land. When it pulled out, you could grow your food. Incredibly important. If you didn't know when it was going to come, no good, right? So a calendar was extremely important. Astronomy and astrology really went together, okay? So it's very important to know when it was going to flood. So you have to develop from there. So here, from there, once the system was developed, now you have administration, right? Taxes. Lovely, isn't it? Even from an early time. So again, like I mentioned, how do you get taxes? Okay, you have to find a suitable and a fair way to administer taxes. Okay? And again, it really comes down to literally measuring the area of a farmer's land. That's how you got taxes. Fairly done. Okay? Written records. Computations done when people started bartering goods. Okay? So a need for counting rows, then writing in numerals were needed to record transactions. Okay? Alright, so one of the things we know about Egypt, and I'm going to sort of move through these fairly quickly because I know it's a lot of information, but what we should know, how do we know anything about Egypt is there's a couple papyruses. There's the Moscow papyrus and also the Rhine papyrus. So I just mentioned about the Rhine papyrus here. It's really the largest and best preserved document that we have, and it was actually discovered through an illegal excavation. But, I mean, it was huge. It was 18 feet by 13 inches, so it was obviously very long. And so we only know a little bit, because only fragments are available. So when we say this is what Egypt knew, or the advanced culture that we know today, we really don't know, because we only have fragments. Okay? It'd be like going through your garbage today, in the future, someone in the future going through and seeing how our life was. We didn't get much. Okay? So we really don't know how much the Egyptians actually knew and how advanced they were. Okay? So in this one here, it begins with a value of 2 divided by the odd numbers from 5 to 100 equals the sum of fractions. So it just gives you an indication how advanced they were. Okay? According to modern mathematics, it's not advanced, but certainly back then it was advanced. Just an example, and again, remember I told you about the scroll and how we only know fragments of it. The building of the pyramids really give an indication how advanced the Egyptians probably were. I mean, don't worry about the math here, but what we're trying to show you is here, these proportions of the pyramid are really 1 square root of phi, which is the golden ratio. That's the golden ratio there. And to the golden ratio, or 3, 4, 5, 1, 4 over pi, and this, again, golden ratio. These ratios were seen in the pyramids. So this gives an indication, like how advanced the Egyptians were to build these things. I mean, it's amazing when you think about it, right? Incredible. They didn't have calculators. They had these ratios in the pyramids. Is it by chance? Perhaps, but highly unlikely. At these things. And obviously the golden ratio and pi was known to the Egyptians. one of the most important numbers. Pi is probably the most important number. Okay? So just give you an example of what we have here. Okay, Egyptian numerals. Another indication, so this is what they use, the single stroke. Another indication of their really advanced mathematics is the fact that they had a character for 1,000,000. Can you imagine 1,000,000? I mean, why would you need a number that big, that time? I mean, think about it, it's pretty incredible, right? I mean, 1,000,000 to us is nothing, because, you know, $1 million, okay, whatever, you know? But back then, 1,000,000 is huge, okay? So, some of the characters they use is single stroke, heel bone, coil of rope, water lily. In fact, if you were going to show a number as 4622, and by the way, I have been to Temple of Karnak. It's in Luxor, okay? And you can see, excuse me, it's 4 water lilies, okay, 4,000, and then 6 coils of rope, 2 heel bones, which is kind of interesting, and 2 single strokes. So that's how you wrote down 4,622. Interesting, if you were to write 999,999, you'd have to have 54 characters, which is too much, right? So the number system had some problems, but it was still pretty advanced. I mean, again, the fact that they had 1,000,000 really is fascinating. Now, interestingly, Ethiopian mathematics, even today in Ethiopia, they multiply numbers very similar to the way the Egyptians did. And so I'm going to bring it up here because I find it fascinating. I told you there wouldn't be much math, I promised you. Okay, but I think you'll find this pretty amazing. Suppose you want to multiply 13 by 17. Okay? What they do over here on the right, on the left, excuse me, they take 13 and they divide 13 by 2. So what's 13 divided by 2? 6.5, right? So what you do is you take the 0.5 out and you put 6 here. Then you take 6 again divided by 2 and you get 3. There's no decimal, so it's fine. And then you take 3 and divide it by 2. What do you get? Well, 1.5, but then you take the 0.5 out and you have 1. Simultaneously, you take 17. You put it over here, 17 times 2, double it, 34. You double it again, 68. You double it once more, you get 36. Okay? Now here's the clever bit. On the left-hand side, wherever the number is even, remember even numbers for you folks? It's like 2, 4, 6, 8, any number that divides by 2. Anywhere it's even, you cross it out. And all you have to do is just add up. 17, 68, 136, and you get 221, which is 13 times 17. Amazing. It always works. And there's reasons why it worked, but I won't go into that. But even today, it's used in Ethiopia. Fascinating. It's been around for a long time. And it's similar to the way the Egyptians did their multiplications. Okay. All right, so let's move into Sumer and Babylonia. Sumerians used a base 60 system numbers. So today we have base 10, right? 0 through 9, because, you know, base pretty much on our digits in our hand. But they use base 60, which is quite fascinating. In fact, today it carries through. Like we have 60 minutes in an hour, 60 seconds in a minute, 360 degrees in a circle. Okay, so there's a lot, right? So that idea still carries forward. So it's called the sexagesimal base, and it probably originated with the Sumerians. So the Sumerians were there before the Babylonians. Okay, and this is some of the Sumerian symbols. Okay, but what I also find fascinating is the Igaki in Western New Guinea also have base 60 numbers. Pretty fascinating. Didn't know that. Remote folks. Not saying there's connections, but they also decided to use base 60 numbers. And here's a clay tablet that shows the powers of 70. Okay? 2050 BC. So, you know, most likely these tablets were like school exercises. Because they used, you know, a stylus, wet clay, and then they poked in the wet clay. Just sort of leave in my mind here exactly what you call that. Cuneiform, that's it. And they would poke it in wet clay, let it dry, and now it would be like your homework. That's what you would hand in. Maybe we should go to that instead of paper, right? So these are often exercises, and those what have survived. So again, what do we know? In total, we don't really know. A lot of it's just garbage. These things probably were thrown away. Can you imagine a little boy that had this cuneiform tablet? Said, oh, teacher gave me good grades. Out it goes, right? Didn't matter, right? So it's pretty funny that these are probably just garbage. the time. And here's the base 60 numbers. It's a lot, right? But you'll find that there are similarities to this and the Mayan culture. Now, of course, the Mayans had base 20, but these guys had base 60. So again, it goes down all the way to 10, 20, 30. You notice some differences. And it ends at 59. Okay? Notice there's no zero. They didn't have it on concept of zero. Now they would say it's nothing. Okay? But they would leave a sort of a spot for zero, but they never had zero as a number. I will talk about why, that's really important. Okay? Why square root of 2? Okay, now, in your old math times, you know numbers, right? 1, 2, 3, 4, 5, 6, so on and so forth. But what about numbers like square root of 2? Okay, so a square root, remember, a square root is, for example, 2 is a square root of 4. Why? Because 2 times 2 is 4. Okay? So now, in other words, a square root of 2, you have some number times another number gives you 2. The same number. Okay? And it's an irrational number. So that's the key. It's not a normal, regular number. Okay? You see, people were using these as practicality things. 1, 2, 3, calculations, okay, measuration. But now, why would you have something called the square root? See, now it's showing what the Greeks are doing, that math started becoming more abstract. Because the square root of 2 didn't really mean much. But this little tablet shows that it's a right angle triangle, okay? And that one side is 1 unit, this side is 1 unit, and this diagonal is the length of square root of 2. Okay? So, and this is just using the base 60 numbers. Okay? So it's actually, people think that the Babylonians discovered Pythagorean's theorem, which I'll talk about in a few moments, but we're not really sure. Again, we don't have enough data to say if they developed that or not. Okay? Okay. So anyway, it's an amazing find. And so it just gives an indication of how sophisticated these societies were. Okay, so let's move to Greece. Yes, this is a Parthenon, but it's actually in Tennessee. This is a reproduction. It's incredible, actually. I love it. I like to go there, actually, in Tennessee. Okay, the Greeks. Now, we've all heard about the Greeks a lot, but for mathematics, they're probably they had most impact of math, of any culture that we know of, and especially in modern day culture as we know it in Western culture. One of the reasons is because the Greeks took, for example, the square root of 2 and proved that it was irrational. In other words, when I tell my students, how is this important? They brought the power of proof to mathematics. So, in other words, going back to the beginning, we talked about space and quantity. So you take basic concepts, you use logical deductions to put them together to create something more complex. Okay? You're building on an axiomatic system by creating proof. And the Greeks brought that to mathematics. It just wasn't, okay, this is what the square root of 2 is. What is it? The Greeks proved that it was irrational. It's a big deal. Okay? By the way, just to give you a quick definition, a rational number, okay, means ratio of integers. Okay, like 2/3, 5/4, 6/1. 6 is irrational. Okay? So if you calculate 3/4, it's 0.75 stop, right? If you calculate 1/3, it's 0.333 repeats, right? So a rational number, the decimals either stop or they repeat. Keep going, but they keep repeating. An irrational number, okay, like square root of 2, never stops and doesn't repeat. Okay? So it's a different kind of number. So what they said is mathematical truths must be proven and math builds upon itself. Through inquiry and logic, they felt that one could understand their place in the universe. Again, what is that like? That's really kind of a religious idea, right? What's your place in the universe? See, it really has the same fundamental roots. It drove mathematics a lot. Most mathematicians and scientists were religious, even in Europe, are up to about Fermat and Descartes. Okay? So it's pretty fascinating. And one of the legacies of Greece that I will show you in a moment is that they wanted to mathematize everything. Whether you agree with that or not, that's the legacy that even stands today. Okay, so let me just go through a few folks as we start moving into getting more into, well, this is not modern times, but say a couple thousand years ago, as we start moving towards our modern day, I'm going to show you some more photos or some, I think, likenesses of folks. Because Pythagoras, that probably sounds familiar to some of you guys when you're in school. Pythagorean theorem, right? It's the same guy. And we don't know if this person actually created the Pythagorean theorem or not. We think he was a bit of a kook, to be honest. But he really was, because he was a leader of a sect, a cult. That's what it was. Pythagoreans were a cult. Okay? And this is their society. They called it acousmatics, listeners, and they had the inner circle as well. What's a great thing about Pythagorean theorems, they included both men and women, and didn't matter, okay, who you were. If you could bring something to the table, you brought it to the table. It was a mathematical sect, religious cult, that looked at numbers as a way of discovering the universe. Very interesting, isn't it? They lived in a society, had no personal possessions, and were vegetarians, which, not good. For me, I've missed that. Okay, but pretty fascinating. So Pythagorean theorem is here. It's a simple theorem, but devastating in its implications, because the fact is, if you look here, what the Pythagorean theorem says, it takes length, okay, of a right angle triangle and translates area to length. It's an incredible thing. It's a simple a squared plus b squared is equal to c squared, right? But it's devastating because its implications, because you use it for everything, including engineering, trigonometry, Euclidean algebra, higher dimensional algebra. It's used everywhere. It's probably the most used theorem in the world. Simple, but extremely useful. Okay, so that's why we can't... Babylonians may have known about it, but Pythagoreans, it's incredible to understand that probably transformed modern day mathematics just with that small theorem, especially with engineering and trigonometry and so on and so forth. And it's interesting, the Chinese had a diagrammatic proof about 600 BC. Pretty interesting. I'm going to show you an example of that when we get into the China section. There's about 367 different proofs, which is kind of interesting. Here's one done by US President Garfield. Kind of interesting. He came up with a quick proof of Pythagorean theorem, so I thought I'd enter that. I thought it was pretty neat. He uses the fact of a trapezoid, takes the area of a trapezoid, sum of the bases and the height, and says this here is half a square, because this is 90 degrees here. Okay, so it basically is half a square, and when you work it out, you solve a squared plus b squared equals c squared. So in other words, you're changing length, a and b and c, and saying its area. Because when you see something squared, right, like a squared, it's this length by this length, understand? It's an area, right? So now you take the area and translate it to length. Okay? It's a big deal, right? I hope that makes sense, because especially with engineering, it's a huge deal. Okay? Euclid. One of the reasons why Euclid's so important is because of his famous book called The Elements. And I'm just going to go ahead and skip ahead here. Well, give me a moment here, I guess. His greatest textbook was The Elements, but let me just go ahead and skip ahead to here. This is Platonic solids. The reason Euclid was so amazing is his book, The Elements, okay, tackled, at the very end, tackled all the Platonic solids. Now, a Platonic solid is a three-dimensional object such that each side is the same object. And that object has equal, each side is equal. Okay? So for example, this triangle is a 60 degree, 60 degree, 60 degree triangle. Okay? And it includes 4 triangles. Okay? And there are only 5 Platonic solids. Now you think about it, right? An engineer or an artist could sit there and try to come up with all different possible models. But in Euclid's case, in his Elements, he showed a watertight argument that there's only 5. There cannot be 6. It's pretty amazing. So when you think about it, this is the real power of mathematics. You take something like this, something abstract like that, and show through using logical deductions there's only 5, not 6. Pretty fascinating, okay? So that's the real power of proof. And this is what the Greeks brought to the topic. Archimedes, I think you've all heard of Archimedes, right? I just bring him up quickly because he's considered probably one of the greatest mathematicians and scientists at all time. And if you think about this guy, he's kind of like, a Renaissance man, if there was such a thing back in the Greeks' times, okay? Because he was a scientist, mathematician, a poet, everything else, okay? But one of the things he talked about, the law of buoyancy, which I talk about in my history of math class, which is quite fascinating, and his discovery of it, okay? Equilibrium, hydrostatic pressure, things that, we know today, but they had no concept back then. The guy's mind was really ahead of his time. People like Archimedes, Leonardo da Vinci, Newton, their minds really only come a few times in, maybe every 100 years, okay, if that. One of his best, most things that he was most proud of was that he showed that the volume of a sphere was 2/3 of a cylinder. And again, I know it sounds kind of goofy or almost like maybe grade 8 math type stuff, but you remember, for that time, it was an incredible achievement. Okay? See, it's easy to look at math now in its basic form and say, well, that's so easy. Why didn't they understand that? But you have to understand, they built these structures upon which we create our complex subject today. Okay? This is just a touching a bit of Archimedes. He came up with war machines. He drew stuff to battle. He was in Syracuse, and he was trying to fight off the Romans. Come up with all kinds of different ways to fight them off. Really an incredible guy. Unfortunately, he met his untimely death by getting killed by a Roman soldier. Okay. I just bring this guy up. Most people don't know about this guy. Eratosthenes. Why I bring him up is, again, another example of kind of like a Renaissance type person, if there was such a thing. Again, an author, a poet, an athlete, geographer, an astronomer. What's fascinating is, in this time, he was one of the first to calculate the circumference of the Earth. And how he did it was this. Here is Cyrene, okay? Cyrene is laid on the Tropic of Cancer. And as you know, 23.5 degrees at, the summer solstice, the sun is directly overhead. So what he did is he took 2 wells. He had a well dug at Cyrene and a well dug at Alexandria up here. Okay, so if the well is dug perpendicular down, right? The sun's overhead, it should go straight down to the bottom of the well, right? So, when that was done, up here, he had a person, when the sun was overhead, at a certain time on the sundial, the person measured the angle of the sun hitting the bottom of the well. And it was 7.12 degrees. Okay? And using basic geometry, like this, he was able to figure out the Earth was about 39,690 kilometers, which is about 2% off the true value. It's amazing, don't you think, from that time? So just an example of the power of using basic assumptions of geometry and mathematics to come up with new ideas, okay, and new knowledge. Okay, last one in the Greeks. I spent a little bit more time with Greek because it is so fundamental, and I'll tell you why more as we move through it and how they affected our culture. But Ptolemy, his view of the universe was wrong, okay? He said, hey, the Earth is in the center of the universe, and everything revolves around it. But, you see, that idea prevailed in Europe for 1,000 years, okay? It's really an unfortunate model. But the thing that Ptolemy did was creating what's called the Almagest. And I'll bring this up again later, because the Almagest gives detail about mathematical theory of the sun, the moon, and the planets. And why is this so fundamental? Because it allowed medieval Europe, who had copies of the Almagest, who knew nothing else about the stars, everything else, allowed them to travel, to navigate. Remember I told you it's hard to navigate? So if you had the Almagest, a copy of the Almagest, which was incredibly detailed, it allowed you to navigate. I'll tell you right now, if middle of Europe did not have that, a copy of the Almagest, it would, it'd be a completely different world today. It would not have been able to navigate. Navigation is incredibly important. And thanks due to Ptolemy. Not saying he wrote the whole thing, he may have just compiled it. But still, it was put into one document. Okay? So this is why I bring this guy up, because he's extremely influential in mathematics and really the science world. So, what I'm trying to show here is, that these developments have created the world we have today. Okay? So I know it's about the history of math, but really it's about history of math and science and how it influenced civilization. Okay? We would not have, civilization today would be completely unrecognizable if we didn't have, the Greeks or the Arabs. And I'll describe why. Okay, so now we move east, briefly. China. Okay, skip China. I don't have a lot on China here, but of course, if you go to my course, I have a big lecture about China. Okay, ancient Chinese number system. Again, they had a base 10 number system, or decimal place value system. Okay, so again, just to backtrack here, a place value system means, for example, base 10. We have a number, right? 234. What's that mean? 2 100s, 3 10s, 4 1s. That's what we call a place value system. Okay, so having a place value system allows you to calculate multiplication and division quite easily. Okay, the Roman system, the Roman numerals. Okay, you ever try to multiply 2 Roman numerals together? It's extremely difficult, right? Okay, so anyways, the Chinese had this system. So I don't know if they developed it independently or with the Indians or what. We're not sure. Okay, but again, they had a base 10, again, place value decimal system. 9 chapters of mathematical art. Again, different culture. Going back to what we talked about before. How did it start? Okay, mathematical theorization. It talks about bureaucracy. Can we get how do we tax people? It's the same thing. The theme keeps coming up over and over again. Okay, the king, the emperor wanted to find out when it's best to, literally, best time to have children. Okay, the astrologers went and looked at the stars. Okay, it's the best time. It's crazy, but that's what it was. I mean, people used astronomy. It was really important for them to know it, so they used it to benefit their society in some respects, whether it was the king or bureaucracy or infrastructure, okay? And what's amazing about this guy is that pi, he calculated this value for pi, which is extremely accurate. Remember, no calculators, okay? He uses Pythagorean theorem, so he had that, didn't even know about that, and what the Greeks had, but they still had this, okay? Leo Hui, fantastic. And this person here, this is also described in the 9 chapters of mathematical art, shows a diagrammatic proof of the Pythagorean theorem. So you can see right here, right? This is 3 length, 4 length, 5 length. Well, if you take 3 squared, it's what? 9, plus 4 squared, 16. What do you get? 25, right? So it just shows you an example of Pythagorean theorem. They don't call it the Pythagorean theorem, the Gauguin theorem, but it's still the same thing. It's credible. And again, what I just mentioned earlier, just briefly, that what this book talks about, surveying and engineering formulas, infrastructure, right? Bureaucratic taxation, oh, wonderful, right? Always the same thing. And of course, computational techniques. Taxation always keeps coming, okay? It's bureaucracy. See, it doesn't matter what society you get, right? If you get a complex society, you're going to see these kind of things pop up over and over again. Other Chinese mathematicians, Yang Hui, I don't know if I'm saying it right or not. You see this? This is what we call today Pascal's triangle. But it was already discovered, way before that. This guy, Qin, I don't know how you pronounce this, Qin Jiu Shao, I guess. But what's amazing about this person, he solved 10th order equations. I mean, the guy was obviously a genius. So, again, really cut off from the rest of the world. China had a lot of amazing mathematical arts that, I just don't have time to go through in here, okay? This here is what we call magic squares, okay, where all the sides sum up to a single number, okay? And you can make any number of sides, 3, 4, 5, 6. There's a certain method to make such that all the sides sum up to one number, okay? So, okay, let's move to India, okay? Happy Diwali, okay? Indian mathematics. So now we're going to move ahead here. Math owes a huge debt, okay, to the Indians, because really our number system we have today was invented by the Indians and really sponsored by the Arabs, okay? But the key was not just the number system, because I mean we could have any number system we want. The fact is they developed zero, okay? And hidden numbers and zero. Actually, the numbers we see today are called the Hindu Arabic numbers. Okay? So, it doesn't show zero here, but in Gwalior, okay, which I want to go visit, shows this number 0. In fact, it was 2, 7, and then 0 was just written a little bit smaller. But clearly, it was a number in its own right. Okay? And people ask, you know, why is 0 so important? Remember I talked to you about before, you know, where the Babylonians would put maybe a spot where 0 was, or they would say nothing is there. Well, 0 is really important because it transformed numbers from strictly, you know, practical aspects to something completely theoretical. I mean, 0 itself is not extremely theoretical in some respects, right? You say, well, you know, if you take 1, subtract 1, it's, you know, 0, right? But because you made 0 a number in its own right, you could start doing mathematical operations on 0. So, for example, what's 1 divided by 0? There's really no solution, right? In calculus, we deal with it. We take the limit from both sides. And if you take the limit from the right side, it's infinity, right? If you take the limit from the left side, it's negative infinity. See, it creates the idea of infinity, okay? The concept. See, it's theoretical, right? So, the idea of 0 being a number in its own right from Brahmagupta, okay, created a theoretical abstract mathematics. See, now mathematics is moving away from just, and the Greeks did it as well, a lot, but it's moving away from just a purely practical aspect to now doing mathematics for its own sake. It becomes a subject on its own. I mean, the Greeks did it as well, for sure. The Romans did not. The Romans just wanted to say, okay, how can we use it to build a bridge? Okay? I mean, that's really why there's no Roman mathematicians that we know about. Okay? But in India, they used, you know, they did mathematics for its own right. And so Brahmagupta said, hey, obviously 0 is a number subtracted from itself. So he talked about something called fortunes and debts. So it makes kind of sense, right? I mean, practically speaking, you know, only positive numbers make sense. But then he said, well, if you have negative numbers, it's like debts, right? So if I owe somebody money, right? So if I owe, you know, Amir $10, okay, I have negative $10, right? It's kind of like that. So that's how he looked at it. So he looked at it as debts and fortunes. So 0 allowed for negative numbers, okay? So remember, you're starting with 0 to 9, right? And now you're increasing the size of numbers, okay, to the negative ones. So it becomes theoretical, okay? Brahmagupta's formula is fantastic, but anyway, I won't get into that. But the key with him, excuse me, is that developing 0 and getting the idea of fortunes, positive numbers, and debts, negatives, okay? Madhava, okay, found the Kerala School of Astronomy and Mathematics. Incredibly advanced things. Why I bring this up, for example, he founded the Taylor expansion series. We only thought that Taylor and Maclaurin had developed this. But actually, it was developed in the, it was seen in the Kerala School of Mathematics documents. Trigonometric functions. Trigonometric is like sine, cos, tan, you know, those things from school, which you all loved, right? Which we're going to study in math, right? Okay. Differentiation. That's calculus. We always thought that calculus had developed with Newton and Leibniz. It did. But, I mean, it's a start, right? Differentiation. Also, integration. This is amazing. You take a series of rational numbers, 1 minus 1/3 plus 1/5, and you get pi over 4. Now, if you guys remember rational numbers? What's pi? Pi is an irrational number. So now you've got a fraction, pi over 4, that's irrational, that is just simply the infinite sum of a rational number series. I mean, you can see it's really developed. See, these people that, did math for its own sake, not just for practicality. It really develops it. Okay? This is one of the reasons why, in the 19th century, why Germany really excelled over France, because France was more concerned about the practical aspects of mathematics, whereas Germany looked at the theoretical. Okay. Taj Mahal, why did I bring this up? Because, I mean, how do you build something like that? You see, do you think it's just easy to sit there and start building, start drawing things out? What do you need? You need a lot of mathematics and science. Just like the Egyptian pyramids, it gives you an indication of how advanced it was. The golden ratio is involved here in every aspect. It's, to build something like that requires an incredibly advanced knowledge of math and, of course, science. Okay? And I've been there now 2 times, and it's just unbelievable. I mean, the second time was even better than the first time. It's just really a peaceful, kind of an amazing thing to see. Because a lot, I think, is because the golden ratio, which I'll talk about in a few minutes what it is, but it's shown a lot in the Taj Mahal over and over again. So it gives that kind of peaceful, it's hard to explain, it's very aesthetically beautiful. Okay? But what I'm saying is, how do you build something like that? It gives you a level, shows you a level of sophistication that they had. Because if you didn't have that, you could not build it. Okay, period. Okay. Now let's move to the Middle East. I promise you, I won't keep you too long here, because the history of math, I said it's brief, but it's kind of long, okay? But this is really important. The Arabic Islamic contributions are probably one of the most important in history. And the reason is because they did translations of the Greek works. Remember, Greece had been long gone as an empire. Then you had Roman Empire, right, of course, and then the Romans, basically the eastern part, the western part fell in 476. Then you had the Byzantine Empire in Constantinople, which became Istanbul. But a lot of the Greek texts were just long and lost. But these folks, okay, because they had such a thirst for knowledge and a thirst for learning, that they actually preserved a lot of the Greek texts. Not just mathematics, but science, poetry, writings, philosophy, the whole works. If it wasn't for them saving those works, our society would be completely unrecognizable today. Guaranteed. We owe them a huge debt. Okay? The Renaissance would not, we wouldn't even know what the Renaissance is. Wouldn't make sense. Okay? Incredibly important these folks saved it. Okay? That's one thing. Number 2, what they did is they took the Hindu and became Arabic numbers, so Hindu Arabic numbers. So they took the positional, decimal, positional place system and utilized 0 through 9. Okay? That's another thing. And last, they developed algebra. Okay, I'm going to talk about that now. I'm going to go back to this one here in a moment. I'm sorry. Okay, I'll get to algebra in a moment, and I'll talk about algebra in a moment. Okay. Here's an example of an Islamic translation of Ptolemy's document. Okay, the Almagest. Remember, we talked about that. If they had not saved that, see, here's an Arabic translation. Middle Age Europe would not have navigated the way they could have. Didn't have the compass. I'm trying to. I can't underestimate. I'm just trying to tell you this is not to be underestimated. I mean, this is extremely critical importance. If they had not saved these documents, we wouldn't be talking right now. It'd be a completely different society. I mean, that's really crucial to understand. So they translated this thing because they give all the positions of the stars, the moons, different times of the year, all the periods of the moon. The sun has a period of 11 years and different ones. All these things were recorded. Okay? It allowed medieval societies to navigate. Okay, so it's just an example of a translation. Okay, so going to House of Wisdom, a lot of it in Baghdad, middle of the 9th century. Again, what do we talk about? Academy, Translation Bureau. So, part of the religion was knowledge is really important. And again, they had the same process as everyone else, government taxation, bureaucracy. But they, again, were like the Greeks and also like the Indians in the sense that they want to learn for its own sake. So again, using mathematics, the Translation Bureau was a big deal, okay? Because it translated not just, again, mathematics, but also philosophy and everything else from the Greeks, okay? So he became a great center of learning. So if you were living around that time, you would go to Baghdad. Probably, if you're in the east or west. That's where you go. Today, no. Okay? But really, that's the key. It's like a big university at the time. Okay? Baghdad. Again, a library, academy, and so on. Okay? Okay, so algebra. Where does that word come from? Well, and I'm going to probably butcher this, but it's Al-Khwarizmi. It's his name, I think it's how you pronounce it. Khwarizmi. He's called the father of algebra. And again, in mathematics, algebra is kind of hard to explain necessarily in a few minutes, but really what algebra is, it's like taking, if you have numbers in theory of numbers, right? You say, this works for this set of numbers. This works for that set of numbers. Algebra says, can we come up with symbols for numbers such that if we do the same operations, it works for every number? That's essentially what algebra is about, okay? So in other words, algebra means restoring, reunion, completion. Al-Makabala, again, means reduction or balancing. Algorithm, algebra, these all come, what have the AL, right? This comes from this guy, okay? Okay, so algebra, okay? It's hard, and so for the development of mathematics, really important person, okay? Omar Khayyam, okay, now, a lot of folks have probably heard of Omar Khayyam. He was a poet, right? Rubaiyat, you guys have heard that, right? The poem. But he's also a mathematician. Look at this. This shows you the advancement of this mathematics. I mean, no calculator, right? And he has the measurement of the length of year to that accuracy. So that shows you not just a high level of mathematics, obviously, but a high level knowledge of astronomy, don't you think? A lot of knowledge. And this is what Omar Khayyam really looked like. Okay, no, I'm joking. This is from a movie, right? But we don't talk about his mathematical stuff. We talk about his poetry, his kind of romantic stuff. And he may have been. But this guy, I mean, he used trigonometry, again, sine, cos, tan, approximation theory. You didn't see approximation theory until Newton. Okay? So, he tried to solve the degree 3 equation, could not, but anyway, they were really heavily influenced by the Greeks because they really thought of geometry and numbers really are together. Okay? In fact, the law of the algebra that you learn today in high school or in school is the methods are from the Arabs, how they developed it. For example, if you hear completing the square, okay, there's a reason. They literally complete the square, they draw it out. Okay? And that's how you have a method of solving a degree 2 equation. Okay? Polynomials. It came from that. See, geometry and algebra, algebra came from geometry. What they're saying. Okay? They didn't believe in negative numbers, which is very interesting. Although the Indians did. Okay. Okay, early Europe. All right, we're moving along here. Okay. Dark, middle, and high middle edges. What I want to point out here is really this. The church. When I say the church, I put a big C, right? The Catholic Church or whatever, Roman Catholic Church. Why was that influential? Because they allowed for universities. Again, remember like how the School of Baghdad, right? House of Wisdom. They were centers of learning. Well, universities became, how they start? They start as religious institutions to train priests. Okay? So, interestingly how that developed. By training priests, they started learning more knowledge. Monks would start translating documents. The same sort of thing would go on, right? So now they would translate it from Hebrew or Arabic or Greek to English, or in this case Latin for that time. Okay, so not just is religion part of the development of mathematics, it's also preserved mathematics and science in interesting ways that people don't realize. And one of the ways it did is through translations. So Latin translations in German, Latin, German, English eventually. Okay. Tally sticks is just an example, just a quick example of how people used. They didn't have numbers, but they used materials like sticks, wood to talk about. You know, if I borrowed some money off somebody, you take a stick, you cut it in half, right? And then when I came back to pay up the debt, they would put the stick together to see if they actually matched up. So it's a very clever way of doing it, okay? So, for example, you can see it here, right? So this part here was given, and this part was given to the other person, and they had to match up. So notches matched up. If the notches didn't match up, then you would see that there could be some sort of attempted forgery. So this is some of the math they did, not the math, but some of the way that they took care of debts. It wasn't until the introduction of the Hindu-Arabic numbers with Fibonacci that we start using numbers as recording things in books, okay? Okay, again, just kind of following from what we talked about with the Arabs and how they preserve a lot of documents. Well, you can see here Greek is translated to Arabic, Latin, right? The same theorem, right? You can see it. So Greek, Arabic, Latin, French, English, Chinese even had some other translations. So knowledge moved around the world. And this is from Euclid's Elements of Geometry. Euclid was, if you remember, Euclid was around a long time ago, right? But this was translated down. Okay, if it wasn't for those translations, we'd have nothing today. Really important. Okay, so early Europe was completely influenced by this. And you can see it was this Leonardo Pisa. He brought the Hindu-Arabic numbers. Remember the Roman numerals, right? Remember those nasty things you did in school? You know, the X's and V's and all that stuff? Well, that's how people did math back then. And how they calculated using an abacus. But with numbers, as we know today, we can multiply and subtract and divide with those things pretty easily, right? So when Leonardo Pisa, or we call him Fibonacci, when he went to North Africa, that's probably where he found the numbers. And he brought them back and said, hey, these are amazing. It's much simpler. I mean, we take it for granted today. Granted that we have our 0 through 9, we're okay, right? But people didn't have it. They didn't have access to those things. They didn't have access to a decimal place value system. He brought the Hindu-Arabic numbers, which allowed for calculations to be done much easier. It's almost analogous to a computer. Transformation. We didn't have a computer, now we have a computer, right? It's kind of like that. That's how transformational it was. Okay? Not to be underestimated. Okay. Fibonacci numbers is something that he may have learned. He's credited to this, but I won't spend much time on this. I have another talk about Fibonacci numbers, but it's just a kind of an interesting pattern such that one number is the sum of the previous two numbers. And what's neat about it and applying it to nature is that sometimes, like for example, in this chamomile flower, that if you look at the spirals, the blue spirals is 21, and the aqua spirals is 13, and this happens a lot. You see consecutive Fibonacci numbers, okay? So for example, when we start off with 1, 1, 2, 3, 5, the Fibonacci number is the sum of the previous two Fibonacci numbers, okay? And it turns out that in nature, you see this a lot. Okay, so obviously, I don't think it was discovered by Fibonacci because it was also seen in the Indian mathematics. But people started, it was part of just applying mathematics to nature. What can we see? Okay, okay. Pacioli, all I want to say about him is, again, just show you the influence of Greeks. Okay, see, he's illustrating a theorem from Euclid. I mean, look at this guy. How what year this is? Again, illustrating a theorem from Euclid. So that is something that it's incredible to think that they're studying these things. If it hadn't been for translations, you wouldn't have had nothing. Okay, father of double entry counting, which Dalian was here. Okay, and the key is here: Franciscan friar. Okay, a monk. So, again, you can see how the church and the universities got started. Really important part of development of knowledge was actually the church in Europe. Okay, we're moving to the Renaissance. Leonardo da Vinci, painter, sculptor, architect, musician. I mean, you can read it all, right? That's what we call a Renaissance man, yes? A Renaissance person that has just basically a master of many things. Well, I would say not a master, but he likes to dive into many of the different things, but really a master of none. But this person was truly amazing, had a truly amazing mind. I don't have much about him here, but his mathematics and engineering, he applied mathematics to engineering, to infrastructure. He developed arch bridges, an idea of a helicopter. I mean, an incredible person. Okay, so, but again, influenced by old Greek works. Remember, what did the Greeks say? They said they wanted to mathematize everything. That legacy still applies today. Okay? It still applies today. Okay, now, well, that's kind of weird how that turned out. Supposed to be lines here, it doesn't show up. Now this guy, it's hard to see, but doesn't he look like an artist? Okay? See, art and math. Now, remember I said about mathematizing everything? Because it wasn't just about, doing math as its own sake. It was applying math to, say, art. And this guy, Albert Dürer, I guess you know how to pronounce it, he created the numbers that we know today. Now, I think it's pretty amazing, right? It actually blew me away, because I always thought it was just some mathematician that created the numbers. But these numbers, I mean, here's from the Western Arabic. How they look. The 15th century, and the numbers that you and I know today, how we write them out, are actually created by this gentleman. Pretty neat, isn't it? Like, look at 4. You can't even recognize it 4 and 5, right? But he created a 4 and a 5. Those numbers are what we know today, and it was created by this gentleman here. Pretty neat. He was an artist, so the numbers were created by an artist. We know that the numbers we know today are created by an artist, which is pretty fascinating. Okay? So that's why I brought him up. Okay. And again, art, perspective. It's not a small thing, right? Perspective in art. It's geometry. So again, applying the knowledge to these. Remember, these guys, Renaissance, they took these documents and just ran with them. So it's like a rebirth. That's what it's called. Renaissance means rebirth. They took these things and they applied it to everything. They took the mantra, let's mathematize everything. Literally. You can say it's right or wrong, but that's what people did. So let's mathematize art. Okay? And it's shown in perspective. Which actually is good in some respects, because it gives you, well, perspective, right? Because it doesn't look weird. Okay? This building back here is not huge, right? It wouldn't look right. Okay? Also, golden ratio, I mentioned this before. It was shown in, remember, the Taj Mahal and other places. But Leonardo da Vinci, he applied the golden spiral to the Mona Lisa. And I was able to see Mona Lisa this summer in the Louvre, right, in Paris. Okay? So the golden ratio I won't really describe, but it really just means it's a special ratio such that the sum of it's split such a way that you have a length A and a length B, such that the sum to A is A to B. Okay? And that ratio is what you saw before, 1.6108, that number. Okay? And that ratio, for some reason, tends to be most pleasing to folks' eye, for some reason. Okay? But, so, because that is the case, they applied it a lot to math and art and to architecture. Okay? Okay, and you can see here, I already talked about the Taj Mahal, and you can see, it's hard to see maybe from there, but this length here to this length is a golden ratio. Okay, so it's a golden rectangle. When the Persians developed it, built it, they put these things into the architecture. Okay? Even here, the Notre Dame in Paris. Again, this length, this is like A and this is like B. Okay? So if you take this divided by that, you'd have the golden ratio. The CN Tower in Toronto, same thing. Is it aesthetic? Yes, perhaps. Maybe it's built on purpose, maybe not. We really don't know, but kind of interesting. Okay, Galileo Galilei, and I'll promise you I'll move along a little bit quicker here. Galileo Galilei, probably the father of modern science. So remember I talked about math and science kind of together? Well, now really math and science are kind of like, they're splitting up. Because as subjects get more and more complicated, now you've got math on its own sake, and science really, which means, the philosophy of nature, right? So that's kind of its own subject. And now math started being on its own, okay? So in this case, Galileo, he was, of course, persecuted by the church a lot. And again, now a lot of these ideas started running counter to the church, whereas before the church supported the birth, really, of knowledge. But now it starts to run counter to some ideas, and certainly Copernican ideas, heliocentric theory. Okay, so instead of stuff revolving around the Earth, as Ptolemy said, right? Now he says, no, actually, the Earth revolves around the sun. That's, of course, against the idea, the structure of what the church thought was true. Okay, so this is a troubled time to live. Okay, but Galilei persevered through it. Okay. And you can see here, he created the telescope. And what you start seeing now, guys, I'm going to say, is now you start seeing, you have this math. Can you apply this knowledge to something in life to improve your life? Whereas before we had a problem, right? We worked out the problem and we come up with math and science to help us deal with that problem. Now it's become the other way, just like we have today. We have this math and science today. How can we take that and apply it to life to improve our lives? This is the start of this. Okay, really important, crucial, it's kind of like the crux of what we have today. Started really with Galileo. Okay, let's move to the birth of calculus. René Descartes. All I want to say about him, he really was a philosopher. Again, a religious person. He said, I think, therefore I am. That's, of course, his famous statement. But I will describe what calculus is in a moment, but this is really started the modern mathematics as we know today. Okay? It really takes off. From this time, from the 17th century and on, it really takes off. Knowledge just explodes. Okay? Provide the basis of calculus for Newton and Leibniz, which I'll describe briefly in a moment. And this is what we call a tangent problem, as you can see this thing moving around here. The idea of a tangent, mathematics at the time was looked at as static. For example, can we find a volume of a sphere, a volume of this, or an area of that? It moved from that to something more dynamic. Can we have mathematics of movement? Okay, it's a big change, right? That's how we get physics. Newton really developed that, but it starts here. And this line, this tangent line, kind of gives you like a direction. Can we talk about that? Okay, we're going this way instead of this way. It's just the mathematics of movement started at this time, which really developed into physics. Okay, Blaise Pascal, again, Renaissance. It's still affected by the Renaissance. Developed mechanical calculator, and a big deal, right? One of the first mechanical calculators ever. Talked about studying fluids. He was the one with, and Tino will appreciate this, probability. Okay, he developed probability theory, at least in Europe. And Pascal's triangle, which was already developed in China. We didn't know about that. But he came up with Pascal's triangle. That's what we call it, Pascal's triangle. Okay? And here's an early Pascaline. It's in the museum in Paris. Okay? Okay, Newton. Now, Newton, everyone's heard of Sir Isaac Newton. He was not a nice guy. Okay? If I told you what I thought about Newton, it would be bleeped out on the camera, okay? Because Newton really was not a nice person, but of course he had an incredible mind, but he was one of the co-developers of what we know of calculus today, okay? So really, it's the differential and integral calculus. They're really two parts of what we know as calculus, okay? But his, sort of his magnus opus is really the Principia Mathematica. Okay, now I'll show it to you here. Here's the actual copy of it. He even had handwritten corrections for the second edition. So this is the actual copy here. But Newton's real genius was science. He really developed physics. You know, the three laws of motion. Okay, you see what was happening? See, they're applying mathematics to life, to, well, it's called the natural philosophy. So, mathematics of movement really, goes into physics. Physics equations are all differential equations. They're all calculus, okay, really. The other thing Newton did is he created a reflecting telescope. People don't know that. That's one of the things that got him into the Royal Society. He was kind of an unknown guy until he sent this telescope in, and they said, well, that's amazing. The idea had been around before, but he was the first one to build a practical application of it. Okay, calculus really briefly. It's just all I want to know about here. It focuses on limits, functions, derivatives, integrals. I'm not going to talk more, much about that. I would spend too much time. But really, it's like it gives a tangent at a point, and a definition of a derivative means it's like an instantaneous rate of change. It talks about rate of change, which is about mathematics of movement, right? So that's really what it talks about, tries to describe. Okay? That's just a very basic part. But without calculus, again, a modern world, we would not know what it's, we wouldn't even recognize the modern world. Okay? Calculus is incredibly important. We wouldn't have gone to the moon for sure, so on and so forth. Without calculus, algebra can only go so far, right? But calculus takes this amount of algebra and crunches it down to like that. Just some really, it's an incredibly important branch of mathematics. Okay? Here's for John, right? And Nadine. It's used in even economics. Okay? Break-even point, revenue, maximum profit, loss. It's applied to, I've seen an econometrics textbook and it just scares me. There's a lot of mathematics in there. Okay? A lot of calculus. So it's applied to everything today. See here, these tangents mean slope. Okay, give you give me a direction, but also gives you a rate of change. How fast is something changing? Is something growing faster and faster, or is something growing slower and slower? It's important, right? So the knowledge of calculus really has transformed, our modern life. We would not, again, have life as we know it without the idea of calculus. Okay, Leibniz really briefly. I got to mention Leibniz because he was the co-developer of calculus, and certainly he was a much different person than Newton. Okay, actually a pretty nice guy. He worked for, he was part of the Hanovers. Okay, not as a person, but he worked with the Hanover government. Okay. And this is an important thing to understand, that royal patronage, support of the arts, the support of knowledge, was supported by royalty. So people like Leibniz had a job. Okay, they were supported by these guys. That's how he got paid. You always probably wonder, how do these guys get paid, right? They got paid by royal patronage. It's really important. Today we have grants and so on and so forth. Okay, that carries on, right? It's really important. So he was supported by the Hanovers. Okay, now Newton really went after him. Okay, because you see, Leibniz published his results of calculus. Newton probably had the first idea of it before Leibniz. But what's interesting is the calculus that we use today is from Leibniz, not from Newton. So I like Leibniz. I don't care too much for Newton, but anyways, very good guy. He created a step reckoner. He also had an idea of a calculator, pretty interesting. So he used base 2 numbers, what we call binary, to solve problems, multiplication, adding, subtracting, so on and so forth. Okay, Euler, we're getting down here. Okay, Euler is probably the most preeminent mathematician of all time, in my opinion. If you guys remember Bayot, he kind of looks like Bayot, you know, our old associate dean, because he is also from Switzerland as well, okay? But he wrote 800 books and papers. Can you imagine? Mathematics. Renowned for his work in mechanics, again, mechanics, mathematics of movement, okay? Physics, optics, topology. I'll talk about that briefly, what topology is. Calculus. Calculus was crystallized in Leibniz's hands. Astronomy, obviously. This is considered the most beautiful formula of all time. The reason is because E, I, and pi are E and pi are considered two really important numbers. I is the square root of -1. It's complex numbers, okay? But if you do E, okay, E for Euler, because he discovered that number, to the I pi plus 1, you get 0. It's really interesting. Yeah. So, it's fascinating. Incredible person. Now, he developed topology. Why do I bring up topology? Because now mathematics is starting to change. I think I've been disingenuous to you folks because I've said about numbers, right? I keep harping on numbers, yes? Well, actually, mathematics now is really not about numbers. It's about sets, okay? I hate to tell you, okay? So if I say the set of all integer numbers, that's what I mean. I don't mean like -1, -2, 5, so on. I refer to the set of all those numbers. Okay, mathematics is about sets. Okay, numbers being a part of that. And topology is sort of the start of that idea. Okay, this leads to something called graph theory, which I loved. Okay, but it really starts talking about how, you know, it gets quite complicated, topology. The fundamentals of mathematics today are based upon topology, and Euler was developed in it. Okay. So these are three other folks that I just don't have time to go over. Gauss, incredible genius, okay? Bernhard Riemann, and also another one. Germany, okay? You see, you don't see a lot of French mathematicians in the 19th century, okay? Except Poincaré, okay? Of course, Poincaré was excellent, top-notch. But Karl Gauss, Bernhard Riemann. Again, Riemann took geometry as we know it today, Euclidean geometry, you know, straight. You know, Euclidean geometry have lots of axioms. For example, if you have two parallel lines, they never meet, okay? Where he said, well, he just took geometry and transformed it to what he thinks it is and what it could be, okay? So, incredible genius. And Karl Gauss just was very prolific in mathematics. Lobachevsky as well. But here, this is the key. Fifth postulate of Euclid elements. He thought, let's change that. Is that really true? In other words, if two lines are parallel, do they never cross? What's that mean? So they came up with the idea of hyperbolic geometry and so on and so forth. So you really start seeing what happens. It really starts to take off in strange ways. Okay? Okay, statistics. Again, I can't talk about. Get Tina in here, right? Francis Galton, Carl Pearson, Gossett, Fisher. Okay, you see now, again, you develop statistics come out of there's problems in society, right? I think it started with Sweden. The Swedish wanted to know how many men they had to fund an army, and they thought they had like 10 million people at the time. So they sent people out to the countryside to count the people, the first census. And they realized they only had about 1.5 million. It scared them, right? I mean, because this was knowledge, right? And they also found at the same time that most women, a lot of women died at childbirth. They didn't realize that. See, statistics kind of crystallizes things that we didn't realize, okay? So the birth of statistics really, you know, statistics come from the word state, okay? So it was really a science of how people, you know, they used initially to say, how do we find out about people and, you know, their average lifespan, you know, how many children die in childbirth, how many, you know, women die in childbirth. It grew from there. So allow the state to really grow into what we know today. Without statistics, we could not have a complex society we know today, without a doubt. Okay, government, we just couldn't handle it, right? We couldn't handle it. So now we're using statistics and applying it onto society, right? Remember I told you? At first it was like, okay, let's find a math to solve our problem, but now we take this math and apply it to society. How can we manipulate statistics to manipulate people? It happens, right? Okay? But statistics cannot be overestimated in its importance. Okay? So I'll just leave it at that. Okay. Group theory. What I say about numbers, we're almost done here, guys. Promise you. Okay? Group theory, what is it about? Well, remember I told you math's not about numbers? It's about sets, right? Well, that's group theory. So, for example, Rubik's Cube can be a permutations of rotations. Okay? It's not about numbers anymore. Okay? So it's weird, I know. So we've shifted from numbers to groups to sets. Okay? So it's a major part of modern algebra. If you take mathematics, it's a major. You will definitely do several courses in group theory. Okay? So let's move on. We're almost at the end. Chaos theory and infinity. Look at this guy. Looks very unhappy. Okay? George Cantor. Now, remember what did I say about the Indians? Remember when we said we had 0, right? What was important about 0? So if you start dividing by 0, it's like, well, I don't know what to do with it, right? It leads to abstract ideas. It leads to the idea of infinity. Infinity is a concept, never ending, right? Whether it's infinitely large or infinitely small. It's really a concept. Okay? And George Cantor, right here, okay, it crystallized in his hands. Because people always had a problem with infinity. Calculus would not be calculus without the idea of infinity. Okay? So the concept had been around for a while. So, okay? So infinity, the idea of it, is incredibly important in mathematics. But he took it and tried to really understand, what is this concept? Okay, it's really a nebulous concept when you think about it. Okay? And this is what he did, a proof. It's just one proof. If you had, to develop, had a chance to, prove one theorem, this is the one theorem that you probably wish you had proved if you're a mathematician. Basically what he said, because when you think of infinity, right, you think, okay, it's very, very large, right? Or very, very small. There's nothing in between, yes? Well, he showed here that the size of infinite sets of rational numbers, remember rational numbers? 1/2, 1/5, 3, 4, 6, whatever. It had, believe it or not, the same size as integer numbers. If you think about that, it's kind of weird, right? Like if you look at all the numbers between 1 and 2, yes, rational numbers, you think there's infinite number of rational numbers, right? Between 1 and 2. But in fact, he set up a one-to-one correspondence by using this diagram. And if you take that diagram and you spread it out like this, you can show a one-to-one correlation between rational numbers and integer numbers. So they have the same size. But if you take real numbers and integer numbers, they have different sizes. Real numbers are larger. So actually there's different sizes of infinity. And so the continuum hypothesis says, is there an infinity between integer numbers and real numbers? And Paul Cohen showed that, well, based on set theory, you can't tell whether it is or not. It's not decidable. We don't really know. It's undecidable. Okay, so it's very interesting. So this idea of infinity is really nebulous. Okay, but Cantor really tried to wrestle with it. Okay, it's incredibly important for mathematics to understand the idea of infinity. Okay, Hilbert, really quickly. Only thing I want to point out about Hilbert is 23 famous problems. 8th problem, Riemann. Remember Riemann? I showed you Bernhard Riemann. His 8th. He talked about the Riemann hypothesis. It's still today unsolved. Okay, whether it's true or not. And he talked about different spaces. So now, remember we talked about at the beginning space and quantity. Well now, okay, we talk about spaces. We think, are there different shapes of space? And him, yes. Einstein said the same thing, right? So think about fundamental ideas, invariant theory, axiomatization of geometry. Okay, quite interesting. And I mean, you get these cubes, right? These are actually real-life cubes. These are supposed to represent a space. So someone took looks like some old exhaust pipes and welded them together. Okay, this is at a museum, well, this is supposed to be a Hilbert cube in Hilbert space, okay? Kind of weird, right? So you come up with different spaces, and people are actually putting them into 3D models, okay? Just one example of many, many things here. Obviously, I don't have time to talk much about them, okay? Computing, what did I say about math being applied to society? Well, you see, now we take math that we know and we apply it to something in society. We get the computer, okay? So this is John von Neumann, Oppenheimer. I will talk briefly about, oh boy, lost my mind here. Alan Turing in a moment, okay? But the computer was developed, okay, using, they saw a problem, they wanted to do calculations quickly. How can they take the knowledge they had and apply it to something? You know what they did? Remember, you have on and off, that's binary, right? It's a base 2 system. Boolean algebra was applied to computers. So sometimes some obscure mathematics is done with no idea of direction where it's going to go. A lot of times, later in years, it'll be applied to something practical. And in fact, it's weird. The more abstract math becomes, a lot of times it becomes more practical. It's kind of weird, isn't it? So Boolean algebra was impractical. It wasn't used very much until it came to computing. That's why we have on, off. Digital, right? That's what digital means, on or off, okay? So apply to computers, okay. Alan Turing, I'm getting close to the end now because, why do I bring him up? Because now math, when we applied math and science, we talked about things of being static and dynamic, but what I'm trying to get to is, we looked at, if I'm given A, I can get B, right? So in other words, if I can see something, and that, okay, I look at it, I can figure everything out about it I can, and then I come to conclusion B. Well, it turns out, what he started was that, no, actually what ends up happening is, real life is about iterations. In other words, you start with something, right? And then that gets mapped onto something, and then that comes into it. You get what you call positive feedback or negative feedback, right? So what ends up happening is you get this small system that you know everything about, okay? But when it iterates several times, the result is something you could not predict. And what's more weird about this is, if you take that initial condition that you had at the beginning, okay, you put it in a 1, just say 1, and you get this result you don't know about. If I take 1.001, I'll get something completely different. It's what's called chaotic theory, chaos theory. Okay? It's 3 iterations. So now it's kind of gone back on itself. See, math and science is about, the world should work like clockwork, right? But in fact, it doesn't. Okay? This is chaos theory, okay? So like the butterfly effect. I don't know why it's not coming up very well here. I'm sorry about that. This is kind of weird. There's actually a part over here. You can see it somewhat here, okay? But it's the butterfly effect. You've heard that, right? The butterfly flaps its wings in, say, Brazil, could cause a tornado in Kansas months later. But could you ever relate that tornado in Kansas to that butterfly? No. Too chaotic. It's like weather. Weather is a chaotic system. That's why we can't predict weather. That's why you have your weather app, right? The weather keeps changing. Because people don't know, right? You can't predict exactly what's going to happen. It's a chaotic system. Because iterative. You see, that's life, right? Systems are iterative. They give feedback. You do something, you get some feedback, right? You walk around, you hear sound, that's feedback, yes? So that feedback changes things. It's like echolocation for a bat. It gets feedback, okay, it's getting too close to the wall, it moves this way, right? So that's what chaotic, it leads to chaos. Okay? So it's a big subject. I have a whole other talk about chaos and infinity. Okay, Mandelbrot, last guy. And it's the last thing that we know of today. The biggest change, latest in modern life that we know of so far is the fractal, the theory of roughness. Like if you look at coastlines, how they're all jagged. Can we find the length of a coastline, or how can we model a coastline of, say, England. Well, how do we do that? Okay, well, it's not so easy, right? And they can but this guy thought that if you can look at take an object and iterate it over and over again, okay? You create, again, chaotic system, you create what's called a fractal. It's a self-similar thing. Okay, it's called something called self-similarity. And we see this with the veins in our arm, in our hands, rivers, coastlines, plants, galaxies. Okay? And Mandelbrot was the first person to think about that. So here's an example of fractal. Here's a triangle. See how it splits? And it creates a mountain. So computers use it because what ends up happening is you can take a simple thing, iterate it several times, and you get this really complex shape. And if you were to change this slightly, just slightly, the mountain will look completely different. See, it's chaotic, right? I have other examples of this. This, by the way, is the Mandelbrot set. Okay? So that's what self-similarity talks about. You see it in clouds, mountains, craters, snowflakes, it's everywhere. Okay? And that's really where math sort of sits today. I mean, there's obviously a lot of details, but that's sort of where we're at today. Okay? So, conclusion, there's basically the how math looks as it's broken down. This, again, is not an exhaustive list, but you can see, I mean, here's rational numbers, integer, natural numbers, fields, rings. This is group theory here. Okay, over here, group theory. Lie groups, okay, general relativity. There's a lot of stuff here. So, you go back to how we started, right? We started from just simple ideas. We put these together through, our natural proclivities of, religion, practicality, because, we want to develop things to help improve our lives, and obviously bureaucracy as we get bigger and bigger in our, groups. Groups get larger and larger. We have to have leaders and governments, okay? So through those simple ideas, putting them together through logical deductions, we create this complex subject we know today. And we have to think of all the cultures that have developed this as we know it today. And you have to think about our modern culture, our modern life, is really, we should thank everyone who has been a part of that. We just can't think, okay, it was just Europe who did it, or the Chinese, or whoever. It was everyone. It really was. So, and I guess the most latest thing, is what we call Millennium Prize problems. These are several unsolved problems. P versus NP problem. This is a complexity theory. I don't have time to go to talk about that. Poincaré conjecture was solved by Gregory Perelman, but he declined the award. Riemann hypothesis, which I briefly mentioned, but it's something about prime numbers. If you can solve the Riemann hypothesis, you will have $1 million. Your picture would put up right in front of, probably ahead of Einstein. If you can solve the Riemann hypothesis, it will undermine internet security without a doubt. If you can prove the Riemann hypothesis. It's true. Very few people think it's not true, but and math is like that. Until it's proven, it's not true. Okay. So, any questions? I know it's a long lecture, I'm sorry. I try to rush through it, but do we have any quick questions about this? Yes?
Okay, you said that for the sets has become an integral part of math.
Yeah, set theory, yes.
And fuzzy math comes from sets. I don't know if it's because I don't really understand fuzzy math.
Well, fuzzy logic?
In the 60s?
I don't. Yes.
Is that going backward or is that proving something?
Fuzzy logic, I never studied that. It's kind of funny because fuzzy math, I actually wanted to study that for my paper. And the professor said, that's not good enough. Don't study that. Study this. Okay? So I don't know much about that, unfortunately. Fuzzy math. I'm sorry. I wish I could talk to you more about that. And you see, I have degrees in mathematics, but you know, really, I feel like the more I know, the less I know. I don't know very much, actually. I mean, obviously I know what I need to know, right? What I've studied, but there's just so much, so many branches, I just have, you know, no idea. So I'm sorry, I can't help with that, fuzzy logic. But, you know, with math, really about sets. It's important. I mean, it's a philosophical idea. If I say a tree, what's going to come up in your mind? It's a picture of a tree, right? You know, it's like, okay, you think of all trees, okay? You have this kind of image in your mind, okay? I understand what a tree is. We tend to group things together, right? All men, all women, all people. We have this sort of image in our mind. And so we categorize things. And so sets are a way of collection. And then we take elements out, which is a piece of a set, and do operations on those sets, okay? So this is what group theory is about. It's about modern algebra, taking the set, let's say real numbers, just our numbers that we know of today. And we apply addition and multiplication on them, okay? So if I take two elements in that set, say 2 and 5.3, what do I get? I get 7.3. That 7.3 is in the set, okay? It's what we call closed under operations, okay? See, math gets more complicated. So we take two numbers, 6 and 7, multiply. What do you get? 42. That's also in the set, okay? So that's what we call modern algebra group theory. Yeah. So we use numbers, but really it's about sets. Now, any other questions? Yes. Of course. No problem.
Do you think we're at the point where we are trying to prove rather than to find? In the sense that instead of trying to develop, we seem to be focused now on trying to prove theories that already existed.
That's interesting. You mean theories in other subjects?
No, in the past there has been a development of a lot of theories in math.
Yes.
But today, a lot of the focus is on not finding new theories, but proving existing theories. Like, for example, if we can solve those problems, it would be quite an accomplishment.
Right. These are what we call conjectures, so they're not proved yet.
Right. Right. But there are no, that I'm aware of anyway, there are no new theories or conjectures that are being proposed.
Oh.
So we're at the point where we're focused on proving or trying to prove, and not so much as theorizing new.
I think I know what you're trying to say. Like, that's the problem with mathematics, I think, is that these mathematicians get their PhD, take some small idea, some obscure location, and just prove this theorem that really has nothing to do with anything else. It's so remote. And so, yeah, it's almost like proving for proof's sake instead of, we got to be careful. We don't want to say it's not useful. It could be useful, right? Like I told you before, but it's not like doing something that's going to be, I don't want to say useful, but it just seems so obscure that it's like their expertise in this a small little area instead of a bigger perspective. So I don't know if that's what you're trying to say or asking about, but old theories, I don't know really about if there's more stuff being proposed or not. Math is sort of, I don't know, I think it's sort of it's starting to limit itself, I think. Because it's getting so complex that, where do we go from here? What's it going to do? How's it going to, improve our lives? Or does that matter? Does it improve our lives? I mean, it's become so big. I don't know. It's hard to say. It can become amorphous almost. Yeah. Yes?
Oh, can you say a little bit about Kurt Good?
Kurt Good. Oh, boy.
Oh, just the denial of the closure of arithmetic or mathematics.
Oh, boy. I have to refresh my mind on that. Yeah. Kurt Good. I have to, again, I know a lot about different mathematicians, but I'm not sure about Kurt Good. I've heard about him, but I don't know much about him. What do you say? Yeah. Okay. Yeah, Grothendieck, you like Grothendieck. He kind of talks, he was a structuralist, Grothendieck, yeah. Are you talking about Gödel? Or Gödel or Kurt Good? Oh, Gödel.
Yeah.
Oh, I thought you said Kurt Good. Okay, it's Gödel. Okay, now I'm talking about Gödel. Ah, it's called the incompleteness theorem.
Yes. Right.
Ah, okay. Good. Okay, I would pronounce it Gödel. Okay. Yeah, Gödel, well, really he showed that the, what I understand is like the set theory, the idea of set theory is incomplete. So, I don't know his exact proof, but basically it's saying that there are certain things that can be proved with set theory and certain things cannot. So if you assume certain axioms, you won't be able to prove everything. So there's certain things that are always going to be left unproven on the basis of set theory. That's the basic idea of it. Yeah. You can't, in other words, there's always an out. In other words, like there's always going to be something that you have to reach out to get something more other than just set theory.
They wanted like a closed system.
They want a closed system, and it's not possible. So a set theory itself is not possible to have a closed system. Yes, and that's really what happened with the Paul Cohen, with the continuum hypothesis. It said it's not, are there infinities between what we know as integer number infinity length and the real number infinity length? Okay, the sizes of infinity. Is there a continuum? And he says, well, I don't know. Based on set theory, we can say yes, we can say no. So basically, you have to, people who do these proofs have to say, well, if we accept the continuum hypothesis, then this is true. If we don't, then this could be true. You know what I mean? So they don't know. Basically, it's not a proof or disproof. It's just like we can't know based upon set theory. That's what Paul Cohen is. So it's kind of like relates to Gödel. In fact, Paul Cohen actually gave his paper to Gödel, and Gödel said, yes, I think it's correct. So Gödel was the one who actually approved that incompleteness, the continuum hypothesis. Because Gödel was a logician. Yeah. Okay, any other questions? Time to eat? Okay, thanks guys.